Hello, today we discuss van der Waals interactions in inert gas crystals. Consider two identical inert gas atoms separated by a distance r, which is very large compared to the radius of the atom. If the charge distribution on the atoms were rigid, the interaction between the atoms would be zero, because for an inert gas atom, the the electron charge distribution around the nucleus is spherically symmetric. So the positive and negative charge centers coincide at the nucleus. Okay. So the potential outside this will be zero. So there will not be any interaction between the atoms. So there is no cohesion. Okay. But atoms induce a dipole moment in each other, and this causes attractive interaction between atoms. This is called the van der Waals interaction. The attractive interaction due to this induced dipoles is called van der Waals interaction. So this is responsible for the interaction between atoms in a inert gas crystals. Now let us consider the two atoms, that is two dipoles, as two identical linear harmonic oscillator with the positive and negative charges with separation x1 and x2 respectively, as shown in figure. Okay, so two atoms there are two atoms. Okay, so the first one is separated by distance x1, and the second dipole separation is x2, and these two atoms are separated by a distance r, which is large compared to r is very large compared to x1 and x2. If p1 and p2 are the momenta, are the linear momenta of two atoms, then we can write the Hamiltonian of the unperturbed system. So we can consider these two as independent. They are not interacting first. So the Hamiltonian of the unperturbed system, okay, that means uncoupled system, that is H0 is equal to P1 square by 2m plus P2 square by 2m plus half C x1 square plus. So here the two atoms are identical, therefore we can write the force constant C are identical for both the atoms. If omega 0 is the unperturbed oscillator frequency, then we can write C is equal to m omega 0 square, where omega 0 is the frequency of unperturbed system. Now let us consider the interaction between the two dipoles. Now let us consider the Coulomb interaction between the two dipoles or the two atoms. So we can write the Hamiltonian corresponding to that is H1. So we can draw the figure here. and the displacement of this thing is x2, this is displacement x1, and the atoms, the internuclear separation of the atoms is r. So H1 is equal to the interaction potential, that is the potential between these two individual atoms, sorry, individual charges. Now this is a induced dipole, these are the two induced dipoles. Now the interaction potential energy is H1 is equal to 1 by 4 pi epsilon 0. So let us consider that atoms have plus E and minus E. So this is, let's consider this two, E square so this is the potential energy. Okay, so this is the interaction potential or interaction Hamiltonian. This can be written as H1 is equal to 1 by 4 pi epsilon 0. So we can take E square by R. Okay, so first term will be 1 plus 1 divided by 1 plus x1 minus x2 divided by R minus 1 divided by 1 plus x1 by R minus 1 divided by 1 minus, so sorry, this is x2 actually, x2 divided by R. Okay, we can use the Taylor expansion for this, expanding these terms, and in the approximation x1 x2, the mod x1 mod x2 are very small compared to the distance, internuclear distance r. Then you can write all these things as H1 is equal to 1 plus, so first one is 1 minus x1 by minus x2 divided by r plus minus 1 minus 2, so minus 2 and divided by 2 factorial, so it will be plus x1 minus x2 whole square by r square. We can neglect the higher order terms, and the third term will be 1 minus x1 by r plus x1 square by r square minus, and the last term will be 1 minus, so this will be minus x2 by r, so this will become 1 plus x2 by r plus x2 square by r square. Okay, so here finally what we will get is 1 by 4 pi epsilon 0. Here minus 2 x1 x2 by r square is there, so minus 2 x1 x2 by r square, so all other term get cancelled, so this thing will be equal to 2 e square x1 x2 divided by 4 pi epsilon 0 r cube. So H1 is equal to minus 2 e square x1 x2 divided by 4 pi epsilon 0 r cube. Okay, so this is the interaction potential or interaction Hamiltonian. In this case, the closest charges are this minus and plus. Okay, distance between these two charges is small, so this potential dominates. So these are plus and minus, so the total interaction is negative. That means it will be attractive. Okay, therefore the total Hamiltonian H is equal to the total Hamiltonian. Total H is equal to H0 plus H1. Here we can consider two types of motion, two modes of motion. One is symmetric motion and asymmetric motion. The symmetric mode of motion is the displacement xs is equal to x1 plus x2, 1 by root 2 times. Okay, so the linear combination of x1 and x2. So displacements are in the same direction. So x1 plus x2. Similarly, the antisymmetric motion is 1 by 2 x1 minus x2, the difference in the displacement. Okay, so this is the net displacement, then it is called antisymmetric motion, xa. Okay, so xs, so the corresponding momenta are ps and pa. Here ps is equal to 1 by root 2 p1 plus p2, pa is equal to 1 by root 2 p1 minus p2 are the momenta. So from using this thing, so these are the displacements. So substituting this in the above equation of the Hamiltonian, the total Hamiltonian will become H is equal to 1 by 2m into P1 square. P1 square is equal to PS plus PA whole square by 2 plus PS minus PA whole square by 2. Okay, plus half C x1 is xs plus xa whole square by 2 plus xs minus xa whole square divided by 2 minus e square by 4 pi epsilon 0 to x1 x2. So 2x1 x2 is xs plus xa xs minus xa divided by 2. Okay, so simplifying this equation, we will get H is equal to ps square by 2m plus half times c minus 2e square by 4 pi epsilon 0 r cube into x square plus pa square by 2m plus half c minus 2e square. This will be plus 2e square by 4 pi epsilon 0 r cube into xa square. So we have separated the Hamiltonian into the symmetric Hamiltonian and the Hamiltonian of antisymmetric motion. So the corresponding frequency of this thing. So we have two different frequencies for the symmetric case and antisymmetric case. The omega is equal to now C plus or minus 2 e square by 4 pi epsilon 0 r cube divided by m. Root of this thing is the frequencies, angular frequencies. We have two values for angular frequency corresponding to the symmetric and antisymmetric motion. So this can be expanded. So we can take this c by m out. Root of c by m into 1 plus or minus 2e divided by 2e square divided by 4 pi epsilon 0 r cube c whole raised to 1 by 2. Using Taylor expansion, we can expand this thing, that is root of c by m 1 plus or minus 1 by 2 into 2e square by 4 pi epsilon 0 r cube c. Next term will be 1 by 2 into minus 1 by 2 plus raised to n is equal to 1 plus nx plus n into n minus 1 divided by 2 factorial square plus xn. Okay. So this will be 1 by 2 minus 1 by 2 minus 1 by 4 divided by 2 factorial. So this will be minus 1 by 8 2e square by 4 pi epsilon 0 r cube c whole square. So this will be, this root of c by m can be written as omega 0. So omega 0 into 1 plus or minus 1 by 2 e square by 2e square by 4 pi epsilon 0 r cube c minus 1 by 8 2e square by 4 pi epsilon 0 r cube c whole square. Okay. Now the unperturbed system has the 0 point energy. U0 is equal to half h cross omega 0 for one atom. There will be two oscillators, that is half h cross omega 0. So that means 2 times half h cross omega 0. When we consider the interaction, then the potential energy is U0 dash is equal to half h cross omega s plus half h cross omega a. Therefore, the 0 point energy due to the interaction is given by delta U is equal to U0 dash minus U0. So which is equal to half h cross omega s plus half h cross omega a minus 2 times half h cross omega 0, which is equal to half h cross omega 0 into 1 plus half 2e square by pi epsilon 0 r cube c minus 1 by 8 2e square by 4 pi epsilon 0 r cube c whole square plus 1 minus 1 by 2 2e square by 4 pi epsilon 0 r cube c minus 1 by 8 2e square by 4 pi epsilon 0 r cube c minus 2 into 1 by 2 h cross omega 0. So this is equal to, therefore this will be equal to minus h cross omega 0 into 1 by 8 2e square by 4 pi epsilon 0 r cube c whole square. Okay, so we can write this thing as, so this is 1 by r, this is proportional to 1 by r cube square. That means this is equal to minus a divided by r raised to 6. So delta u, so this is the potential energy change or 0 point energy due to the interaction, is equal to minus a divided by r raised to 6. So that the attractive interaction varies inversely as the sixth power of the separation of the two oscillators. This interaction is called van der Waals interaction. This is also called the London interaction or induced dipole-dipole interaction.